This is the first problem that we are going to do. Now we have a long beam which is made up of two beam elements of length L by 2, identical. Both have modulus EI, and I have numbered them as 1 for the left element and 2 for the right element. So they are exactly identical and also oriented along the same axis. So both of them will have the same local stiffness matrix. And how do I get this local stiffness matrix? This is the stiffness matrix of a beam element, and here I will just replace L by 2 because the length is now L by 2 as given in the problem. So both your elements 1 and 2 will have this stiffness matrix, which I have got by replacing L by 2, L with L by 2 in the previous expression. Now I will have to assemble it to get the global stiffness matrix of this super element, which is composed of two local elements. Now to do that, I need the destination array. I know there are 2 degrees of freedom per node. So here the degrees of freedom, the global degrees of freedom for this node 1 is 1 and 2. Global degrees of freedom are 3 and 4 here, and 5 and 6 here. So for element 1, this is local degree of freedom 1, local degree of freedom 2, 3 and 4, and I have local degree of freedom 1 going to global degree of freedom 1, 2 going to 2, 3 going to 3, and 4 going to 4. So this goes to, by the way, I have 3 nodes, 2 degrees of freedom per node. So my K global will be 6 cross 6. K local, of course, is 4 cross 4. So this goes into the top 4 cross 4 corner of the global stiffness matrix. So that's where it goes. It goes into columns 1, 2, 3, 4 and rows 1, 2, 3, 4 of the global stiffness matrix. Okay, the second element also has okay, the second element also has the same local stiffness matrix. So this is local 1, local 2, 3 and 4 as before, but the degrees of freedom, the global degrees of freedom that it goes to is 1 goes to 3, 2 goes to 4, 3 goes to 5, and this goes to 6. So this goes into this part, of the global stiffness matrix. And you would see that for degrees of freedom 3 and 4, the stiffness contributions from element 1 and element 2 will add up, whereas for 1 and 3 there would be one would be stiffnesses only due to element 1 and 3 would be only due to element 3. What about the force vector? The force vector, there's one force in the negative direction at degree of freedom 3. So remember, the forces are force, moment, force, moment, force, moment. So this is a force which has to be applied at degree of freedom 3, and its magnitude is minus p. So the force vector will be 0, 0, minus p and 0, 0, 0 everywhere. And displacements are of course v1 theta 1, v2 theta 2, v3 theta 3. This is the global displacement vector, out of which we know that v1 is specified to be 0, v3 is specified to be 0, because both of these ends are supported on rollers, and the displacement in only the vertical direction is restrained. So this and this will have to be 0, and we will have to impose that boundary condition now on this global stiffness matrix. Remember, this global stiffness matrix at this moment is equal to is singular at this moment. Okay. Now to impose these boundary conditions, what we have to do is the first specified displacement is 0. So I have to multiply the first column with the first specified displacement. So I multiply this with 0, take it to the other side, subtract it from f. So since this is 0, I have to subtract nothing and f remains as it is. If this was some given value, as in the second problem in quiz number 3, it was a given value. So you'll have to multiply this by the given value and subtract it from f. In this case, we get zeros all over, so nothing is subtracted. Similarly, for V3, we have to take the third column, multiply it by the specified displacement, which is 0 again, and take it to the other side, subtract it from f. Since it's 0, nothing gets subtracted, so f doesn't get changed. And then we will have to make this first row, first column and first row completely equal to 0, and third column and third row completely equal to 0. Replace this by 1, replace this by 1, so that the first and the third equations become identities, and I get the modified K matrix, which we had earlier called K prime, the K prime matrix with the information about the boundary conditions built into it. So this is the K prime matrix with the boundary conditions built into it. So I made a mistake. I'm sorry. The second degree of freedom is V3, but it's the 1, 2, 3, 4, 5, fifth degree of freedom. So it is not the third. It is not the third row and third column. I'm sorry. I made this mistake. So this, of course, goes, and 1, 2, 3, 4, 5. This one goes, and this one goes. You make this one, you make this one as well. So the modified stiffness matrix now looks like this. So this is 1. So the first equation has been reduced to an identity, and this is equal to 0, and this is 1, and this has to be made 0. It is 0 already, but if it is not 0, then you have to make this force, the first force, equal to 0, and the fifth force equal to 0. So when you calculate the F prime matrix, the modified F matrix, you multiply by 0 the first column, you multiply 0 the fifth column, and take it to the right hand side, subtract it from F. Since it is 0 for both cases, you subtract nothing from F, and F remains as it is. And as it turns out, this and this are anyway 0, so you don't have to replace them either. But if they were not 0, you would have to replace them by zeros, so that you now have an identity for the first and the fifth equation. So this is what you have to do. Now you can solve the system if you know the values of L and EI and P. You can solve the system, and once you solve the system, you can find out the stresses at any point in the system. So how do we find out the stresses? That's in the next lecture. Now let us imagine that we have solved this system, applied boundary conditions on the left and right, and solved this. So we have the solutions to all these degrees of freedom, with V1 and V3 coming out to be equal to 0 because these are identities, and the rest of the degrees of freedom I know. Now I can go ahead and find the shear forces and bending moments. So to do that, let us assume that we have a generic element E, right? And at degree of freedom, local degree of freedom 1 of that element, I have M1, I have theta 1 and V1 as the degrees of freedom that have been already determined, and corresponding to them, M1 and F1 are the moments and forces respectively. I have taken a cut somewhere at the middle of the element at a distance x from node 1, and of course when I take a cut I have to apply a shear force and a bending moment. So when I do that, if I now do a moment balance of this, I will see that F1 times x is a positive moment outwards from the plane. M1 is also a positive moment, and then m at x is a negative moment. So this has to be equal to 0. And similarly, V1 minus Vx also has to be 0 from force balance in the vertical direction. So now I have F1x plus M1 is equal to Mx. So this is my equation for Mx. And in place of F1, I can now go back to these equations and I can find F1 as I can go back to the equation for element number 1. Let's say if E is equal to 1, I go back to this equation and then I have U1 which is known now, V1 which is known now, theta 1 which is known now, V2, theta 2, all this are known. So this has to be equal to F1, M1, F2, M2. I know this, so 12 times V1 plus 6L by 2 times theta 1 minus 12 V2 plus 6L by 2 theta 2 whole times 8 EI by L cube will be equal to my F1, right? And M1 would be 8 EI by L cube into 6L by 2 plus 4L by 2 whole square minus 6L by 2 plus 2L by 2 whole square equal to M1. So this would be M1, this would be F1, out of which we know that V1 of course has to be 0. Sorry, this is into V1 into theta 1 into V2 into theta 2. Forgot that. So out of which I know this is 0 anyway because V1 is always equal to 0, and the rest of it gives me F1 and M1. So if I now rearrange it, this is what I will get. In our case, V1 is equal to 0. I have kept the V1 because V1 may not be 0 for every element. And this will be the expression for Mx. Similarly, using this, you can find out the expression for the shear force Vx. Now, for the second element, if E is equal to 2, then V1 is not equal to 0, but then V2 is equal to 0 for the second element. So this term will not be there and the rest of the terms will give you Mx, and similarly you will get expressions for Vx as well. So this is how we solve for the bending moments and the shear forces after we have got all the displacement. So what we do is, after we have got the displacements, we go back to the local stiffness equations for each element, and so we go back to this and then plug in all the degrees of freedom for that element. All degrees of freedom for that element, do the multiplications to get F1, M1, F2, M2. So this is how you determine for each and every element, you determine what is the bending moment and shear force at any position within the elements. Okay, so the idea is, though you have found the values only at the nodes, going back to the local stiffness equation, you can find the values of shear force and bending moment at any location in between the nodes as well. So this allows you to